So now let's say we are looking for a plastic increment. So in the plastic increment, as we've already discussed before, once the yielding has occurred, then you have to consider a sampling point which satisfies this yielding criteria, right? So let's say the yield function Fa becomes equal to 0. So at the stress state A, you have yielding. And what you want to find out is the stresses at the stress state B for the current increment, at the end of the current increment. So if you have to find out the behavior after yielding, then you need to bring in all the plasticity conditions that we have discussed before. And what we need here is the plasticity multiplier. So we are going to use the plastic strain increment for the step AB with the flow rule, which was given as the change in plastic potential with the stress in terms of the plastic multiplier, where the plastic multiplier has already been defined for you before as the P lambda matrix with the strain increment. Now, of course, P lambda is used as an initial guess, which is estimated at the point A, which is the stress state A. So if the delta lambda is less than or equal to 0, then you have unloading that happens at the end of the step, and we can get the stress or the trial stress at the end of the increment as sigma A plus E delta sigma AB, and that you would get it as sigma trial or the sigma B in this case. But if in case your multiplier is greater than or equal to 0, then the step has become plastic. So if the delta lambda is greater than or equal to 0, we have plastic conditions, which means that we must evaluate flow rule. So we have the question of evaluating the dou q dou sigma, which varies along the path A to B. But the question is, how do we calculate this variation? Because we have some information from the state A, but we don't know anything about the state B. So the general way of doing it in a multidimensional formulation is that you have your change in strain from A to B for plastic condition to be given as a certain fraction 1 minus gamma times the flow rule at state A times P lambda at A plus a fraction gamma with the flow rule at B, P lambda at B, all of this with the total strain increment. Now, if I use gamma to be equal to 0, then I am completely using the initial state. That means the final state is not being used at all. If I use gamma to be equal to 1, then I only use the final state and not the initial state. But the final state is not known to me. So the equation is therefore either going to be solved explicitly, which is the forward integration over here. This is explicit, so we use all the required information from the previous step, and you can have implicit when you use it from the second step. But in the implicit case, you don't know the endpoint information, so you solve it by means of a predictor-corrector format. The predictor uses the start point information to first obtain the first estimates of the plastic strain increment and the stresses, and then keeps iterating it in order to get the right solution. And of course, to get the right solution, you need to use a smaller size of the load increment so that you can use a better you can get a better estimate for every increment step. Now the other method is also sometimes we use the gamma to be equal to half, but then in that case we have to make sure that we have to use very small size of the load increments to get better approximate solutions for sigma B. Okay, so that is one of the conditions where you have plastic increments, and of course you see that it becomes more and more difficult when you have to go into the plastic increment because we don't know about the final state of stress, and hence a number of other numerical techniques have to be used in order to solve this equation. Now we've already discussed all the different possibilities of plasticity, staying within elastic range, crossing over to plasticity, etc. I already told you that when we are looking at calculating a plastic stress for the condition of moving into plasticity. So if we had to find out a sigma b, which was a function then of sigma a plus a certain fraction of the gamma with respect to the stress, the strain that we were calculating. And I also said in some cases we also use gamma to be equal to half. Then I'm going to just pick this example for the ease of writing it. Then I can have the sigma b is equal to sigma a plus half of delta sigma ab1, which is going to be the first increment, of course, and then the sigma ab2 for the second part by using half and half. So we use the average of the two estimates, and we get a certain sigma b. And of course this sigma b comes with some error. Now this error can be reduced by means of reducing the size of the increment, because this equation seldom gives you a good result in the first step itself. So what you need to do is you need to get the current load step to be subdivided in order to get your first stress increment. This small step should be causing the yield function to change by more than about 10%. Okay, so you need to divide it in such a way that your f yield function has an increment of more than 10%. Let's say increment, so delta f I can write to be more than 10%. Only then you should use the current load step, which is subdivided into some smaller number of steps. Another way to calculate the number of load steps that you should use is relating it to the error of the initial estimate stress, which would be, let's say, an initial estimate stress sigma b1. So let's say you have an initial estimate stress sigma b1. Then if you remove the sigma b from it, which comes from over here, this one, then I would get, then I can use this as an error. So this is delta sigma error. Then if I use this error vector in such a way that I have delta sigma error divided by the sigma e, which is the, for the one Mises case, is the effective stress, times 2, then I would get the number of steps that I need to make, the number of steps or increments to be equal to 20 times this value e. So that would give me a good estimate of how I can reduce the error by using very small increments so that I can get a better estimate. This was just a flavor of how you can do it. So I cannot tell you that this works for every problem. This is an example for the one Mises stress.